First of all, it's an announcement. Next week is going to be a quiz at 9 a.m. I sent you an email this morning. So it's next Thursday, 9 a.m. this place. It's quiz for this group and also for the group that I'm teaching statistical mechanics in Hebrew. So the quiz is on the first 4 lectures, basically covering all the material about thermodynamics and thermodynamical phase transitions. Basically, it should examine you on the knowledge of class material and also the home assignments. Basically, going to be one question, similar or somewhat similar, I should be less precise, to one of the questions that you got home. That's it. I just remind you, so each quiz, it's 11% of the final grade. Okay, so where do we start today? We're continuing. We're continuing with the micro-canonical ensemble. And we've seen last week that, well, it's very easily defined. The only definition that we needed, well, a constant energy. And we had an assumption that if we have a constant energy, so all the possible states are the states with the same energy, and the probability to be in one specific state is just 1 over the total number of the states for the system. So it's very easily defined. We also defined the entropy. Just remind you, S was K Boltzmann Ilan over logarithm over all logarithm of number of states with this specific energy. And by using this definition, we could obtain all the macroscopical functional states, right? The only thing that we needed to do is to actually count all the number of states, calculate this guy over here, right? Perform a logarithmic, take a logarithm of the number of states, obtain the entropy, and the moment we have entropy, we can obtain free energy, we can obtain temperature, we can obtain the enthalpy, etc., etc., etc. The problem was that each time we encountered in a somewhat difficult, we were in a difficult spot. We actually were obliged to calculate this guy, which was a combinatorial problem, and for examples that we use in class, well, it was very simple, right? The problem is that real-life situations are much more complex. Take, for example, the two-state model, right? So in a two-state model, we had two energies, 0 and epsilon, and each particle could be only epsilon or 0. And then it was pretty straightforward to calculate the number of states. But if I would increase this problem a little bit by adding, instead of E, it's going to be 1, and we'll add another state, E2. To solve this combinatorial problem, in order to state what is the number of states for a given constant energy, it's really, really hard already. And if I would do this for 4 particles, it becomes even more harder, etc., etc., etc. So, there is a somewhat problematic part to this micro-canonical ensemble is that, well, counting states, it's actually difficult when the problem is more involved or more complex than what we encountered before. Another problem, so this is actually a somewhat technical problem, right? Because well, we have a combinatorial problem. It's a math, very defined mathematical problem. Either you can solve it, either not, but it's something mathematical. There is also another difficulty here, is that, well, how many actually the states? So we need specifically to give an energy, a constant energy, such that all the states will satisfy this given energy. But it's nobody actually assures us that for a given general energy, there be any number of states that actually satisfy this constraint. Okay? we don't know if we'll just provide you what is the energy. If I will give you just some abstract energy, here I will give you a number, 72 joules. How many states satisfy the 72 joules problem? I don't know. I actually need to go and check, and it will eventually see that in order to satisfy this constraint, it implies that epsilon 2 and epsilon 1 should have some specific values, right? And it's not always the case. So for example, Einstein model we have seen that each particle had an energy of n is an integer number, h bar omega 0, right? Okay, and the total energy was a sum over I, and I goes from 1 to 3 n bar. N bar is the number of atoms, 3 n bars. It's because we had 3 degrees of freedom per particle. So this was the total energy. Okay. Now, so the constraint that we had to satisfy all the time is that this guy over here should be equal to this guy over there. Right? So let's look on example with 2 n's. Okay, so basically I'm looking only at a specific example when I have 2 degrees of freedom. So I have n1 and I have n2. Now, what are the possible values of n1? It could be 0, right? It could be 1. It could be 2. All the integer numbers up to what exactly number? Up to some number that actually is given by the total energy in the system, right? So what is the edge situation? The edge situation that n1 has all the energy and n2 has no energy whatsoever. So n1, its maximum value is u, the total energy, divided by h bar omega 0. Okay. Somewhere over here. The same goes for n2. It could get number 0, okay? Get 1, 2, 3, etc. Up to what value? Again, the edge situation. All the energy is in n2, n1 has 0 energy, so here it also goes up to u divided by h bar omega 0. Okay. Now let's plot all the dots that are actually possible states of the system, regardless of what is the total energy. So we have n1 can be 1. So those are the states, right? Those dots that I'm plotting. What is a state? Is basically a situation when n1 is an integer and n2 is an integer. So here I plotted in this blue dots all the possible values of n1 and n2 together. What is this constraint? The constraint that u equals n1 h bar omega 0 plus n2 h bar omega 0. Okay? Or u divided by h bar omega 0 equals n1 plus n2. So this constraint here that reflects that n1 and n2 are not completely uncorrelated is that we have a specific line that goes from this point over here to this point over here. This is a straight line. And all the states that actually satisfy this constraint are the states that are sitting exactly on the line described by n1 equals minus n2 plus u divided by h bar omega 0. Okay, so what are the states that we have seen here? Well, maybe this state and this state and this state. Okay. But imagine that I can actually have a slightly different u. Okay, I can have a slightly different u that will cross, that will not satisfy any state. I can imagine a line that is parallel to this line and actually going through all possible states of n1 and n2, and there is not even a single state that satisfies this constraint. Why is that? Because my states are discrete. My states are always discrete in this model and almost in the majority of the quantum problems. So in the micro-canonical ensemble, when I have a specific constraint that the energy is constant, I can obtain a situation that, well, I change my energy by a little bit and I have several states that actually satisfy this constraint. And I change my energy a little bit again, and what I get a constraint that does not satisfy any state. So basically when I'm starting to count states, I need to count this number. This is omega e. What is this omega e? It's exactly the number of points that are satisfying my constraint. I can obtain a very peculiar situation. I can obtain for a specific energy, I have some states. I change my energy by a little bit, and I have no states whatsoever. Right? So this is a problem. This is a problem of micro-canonical ensemble. It's not only that it's difficult or might be difficult to compute this guy, it's also that this guy can behave in a very peculiar fashion. You change it a little bit, you modulate your constraint by small amount, right? And then suddenly it does not satisfy any situations. So how you solve it? So well, we are going in the following direction, saying, well, actually, in order to define the micro-canonical ensemble, what we need to do is not only define the energy and not only count the states that are exactly on this energy line, okay? We should define some specific delta, which is a width of my line, okay? So now it's not a one-dimensional line, it's a two-dimensional rectangle or something. And I will count my states as all the states that are sitting inside this area of width delta. Right? So now I should have, in order to define micro-canonical ensemble, I'm saying, well, I'm not looking only on the states that are satisfying this constraint. I'm also looking on the states that are in nearby region. Of what size? Of some size delta, and delta is not zero. It might be small, but it's still non-zero. Well, in this way, I somehow overcome this difficulty, right? I have this delta over here. But you see that I'm actually starting to wiggle around about, well, the constant energy thing. It's not exactly constant, it's also some small variations around it. Well, maybe it's actually physically well defined. Why? Because I already told you that when I'm looking on a quantum system, I can never say that it's in a specific state with a specific given energy. Why? Because if a quantum system sits in a state where its energy is known and it's an eigenstate of the system, it will never go away from this state. It will never start to sample all the other different states of the system. It will be stuck there forever. Why? Well, this is the solution of Schrödinger equation. This is how we know, or how we assume, that the world actually behaves. So what are the usual comment on this? Well, actually the energy physically is never constant. You always have some small interactions, even with the vacuum, when there are some vacuum fluctuations. So there is always physical, some small delta. It's not always a specific epsilon. It's some energy plus some delta around it. So maybe this is good, right? But still, now we are still in some problem that we need to count the state, well, maybe not on a specific line, but in some small region delta around this line. But actually, it's a little bit of a good thing. Why? Well, because the moment I have a specific delta, I can say, I don't really need to count all the states that are sitting on this line. What I can do is to perform the following thing. If I have n1 and I have n2, okay, and this is my constraint. This is n1 equals u divided by h bar omega 0 minus n2. Okay. So, and those are all the states that are below this line. So in order to compute all the number of states that are sitting in some small region here, right, what can I do is to compute all the numbers of states that are below the line, and I can also compute all the number of states that are below the black line, okay? And I can take a difference between those two, right? So the number of all the states that are below the original constraints, I will call it omega bar of u divided of u. Okay? And all the number of states, so this is below the purple line. And I will call omega bar u minus delta number of states below the black line. So omega of u without the bar, omega of u without the bar is what? Well, it's only the states that are in the vicinity, in delta vicinity of the original constraint when the total energy is u. So all this region over here. It's now easy to actually compute it because omega u is simply the number of states below the purple line minus the number of states below the black line. So let's write it down. It's omega bar of u minus omega bar of u minus delta. So it's a little bit easier to actually compute all the states below the constraint and all the states below some additional constraint and just take the difference. It's mathematically easier. What I'm going to show you that when the number of the particles in our system is very, very, very large, actually we don't really need to perform any differentiation whatsoever. We will see in a second when the dimensionality of our system, so the number of the degrees of freedom, is very, very large, what we'll see is that this guy will be exactly equal to this guy. Okay. What we actually need to do. So it's very easy to understand what I'm saying here when we are looking only on the number when we have 2 degrees of freedom, n1 and n2. What we are actually going to perform, we're going to increase the number of the degrees of freedom. So if we are using u and the total number of the degrees of freedom was 3n bar, we're going to take, and now we had 3n bar equals 2. Now we're going to take 3n bar goes to a very, very, very large number. So basically, in 2, what I need to compute is the total number of states below some specific line. When I have, for example, 3 degrees of freedom, it's basically only one atom. So I will have n1, n2, n3, the line of constant energy is what? It's now not a line, it's a plane. Okay, so here we have u divided by h bar omega 0. Here we have u divided by h bar omega 0. Here we have u divided by h bar omega 0. What we do is we connect this by a plane in our three-dimensional space. Okay. This is our plane. And if we want to use this method again to define the number of states, so what we had to do originally, we originally had to actually count all the states that are exactly sitting on this plane. Okay? Now what we are using not only u but actually a small delta vicinity of u. Okay? What we need to do, we need to calculate the number of states that is bounded by this plane and the planes of the cube. So the planes were n1 and n2. Okay, so basically one octangle of the three-dimensional cube. Okay, so what we need to compute is all the states that are lie below this plane, two-dimensional plane. Right? So this is our goal, and not only do perform this for three dimensions, we need to perform this for 4, 5, 6, 7, and generally n-dimensional space because we have n degrees of freedom. Okay, so let's start with calculation of omega bar of some specific u. Okay, because if we know how omega bar for specific u behaving for general u, we can also pretty much very fast to calculate omega bar for u minus delta. Take the difference and compute the number of states. And I will show you that as the number of states grows, those two guys become almost similar to each other. All right. So how we do this? Well, we are using the Einstein model as an example. Be using the Einstein model as an example, and we start with 1 degree of freedom. So Einstein model, 1 degree of freedom. What do we see? What do we know? U is equals always to n1 h bar omega 0. So if this is n1, it can get what kind of possible values if the total energy is u. So it can get 0, 1, 2, 3, up to what value? Up to u divided by h bar omega 0. Right? So it's bounded above by this line of total energy divided by h bar omega 0. We want to compute omega 1, it's only for one dimension, of u, which is basically to count all the states that lie below this line. Okay. So this is 0, 1, 2, 3, 4, 5. So if we are assuming that this energy is not an integer, but it actually lies below, we can say that the number of states plus minus 1 is equals to u divided by h bar omega 0. Okay? We just count all the states all the integer numbers that are lying below this line. Okay? Right, so this is omega 1. Now we go to omega 2. It's in some sense a proof by induction. 2 degrees of freedom. U equals n1 h bar omega 0 plus n2 h bar omega 0. This is our constant energy. So what we have, we can plot our line. This is n1, this is n2, this is the line, this is the line of n1 equals u divided by h bar omega 0 minus n2. And we need to calculate all the different states that are below this line. Basically, a lot of different states that are lying here. And I need to count them. And there's a lot of them. So instead of counting one by one, I'm simply saying what I have done here. I counted the number of states, but I also represented it as what? As the total length of this line that is starting from 0 and lying and going up to u divided by h bar omega 0. So I basically stated that the number of states is the length of this line. The same assumption I'm going to make over here, saying the number of states is proportional, right, to the area below this line over here. This is the area is equals to the omega bar of u. Omega bar 2, because I have already 2 particles over here. So what I have over here, instead of counting different number of states, I'm going to integrate in order to calculate the area and afterwards the volume. I'm going to integrate and calculate the total area of this rectangle. So we all know how to calculate this area is this guy multiplied by this guy divided by 2, but let's do this in an integral form.
But the area will give you the exact...
It will give me something that's proportional to the number of points there.
No, because in the first one was exact.
It's not exactly exact, because if u divided by h bar omega 0 is not an integer, it's also not exact, right? We have some small error over here. Okay, so it's proportional. Exactly the same, this is proportion. Now, am I actually wrong in doing this? Not exactly. Why? Because I'm afterwards going to work with entropy. So if I have some proportion over here, so it's u multiplied by h bar omega 0 multiplied by some constant. Taking a log of this constant will just give me some additional something, value for the entropy, and it's constant. I don't really care about it. Okay? So it's an approximation, but it's a very good approximation, especially when I'm going to talk about high-dimensional spaces and volumes. All right, so how I represent this integral over there. So what I'm going to say is the area, general area, so omega 2 of u, is what? An integer, and one goes from 0 up to u divided by h bar omega 0, right? Because this is n1, it can actually change from this point where it's 0 up to this point where it's u divided by h bar omega 0. The same goes from n2, it goes from 0 up to h bar omega 0. Right? So I have a double integral from 0 up to u divided by h bar omega 0.
But if you use integral in the 2-dimensional problem, why you don't use the length in the first dimension?
What? Well, I can also say what is the length of this guy. Hey, I can say exactly the same thing. You're absolutely right. I can say, well, what is the length? Okay, let's do it here. So omega 1 of u is as an integral from 0 up to u divided by h bar omega 0 of dn1. Right? And it's equals, what is this integral? It's simply u divided by h bar omega 0. So you're absolutely correct. It's exactly the same result. Exactly the same result. So actually we did it there. I told you that I did it, but I actually haven't written it. So you're right. Now here I had an advantage. I had only one variable. Here are two variables. An area is dn1 multiplied by dn2, but I have a constraint. What is the constraint? The constraint is that actually the upper side of the integration should satisfy what? Should satisfy that n1 equals, or n1 plus n2 is smaller than what? Than u divided by h bar omega 0. This is my constraint. So I'm not integrating this whole area, rectangular area over here. I'm actually integrating the area that n1 can change between u and h bar omega 0, n2 can change between 0 and u divided by h bar omega 0, but I also, at any point, have to satisfy this constraint. So I haven't got rid of this constraint, it's still there. Okay. So let's continue. So I have integration between 0 and u divided by h bar omega 0 dn1. Here I have an integration between 0 and n2 goes between 0 and u divided by h bar omega 0 minus n1. I am explicitly introducing the constraint into the integral. And I have here dn2. So let's take this integral. This integral stays the same. It's 0 and u bar divided by h bar omega 0 of dn1. And this integral over here is simply u divided by h bar omega 0 minus n1. Now what should I do? I should take u divided by h bar omega 0 outside. Okay. It's equals u divided by h bar omega 0 integration between 0 and u divided by h bar omega 0 of what? Of 1 minus n1 divided by u divided by h bar omega 0 dn1. This guy is simply omega 1u. Okay. So this is omega 1 of u multiplied by 0 to u divided by h bar omega 0 of 1 minus n1 divided by u h bar omega 0 dn1. Okay. And when I integrate over this guy, what I will get? I will get omega 1 multiplied by 1 over 2 of what? Of u divided by h bar omega 0. Okay. This is what I will get eventually. And this equals to 1 over 2 omega, this is bar. This is bar, and yeah, this is bar. So this is omega 1 bar of u multiplied by 1/2 u divided by h bar omega 0. And here I have u bar multiplied by omega 1 u bar And what I have obtained is that omega 2 of u bar, so this is this whole area, this was omega 2, this whole area, which is the number of states below this purple line, which is defined by u, is equals 1 over 2 factorial omega 1 of u to the power of 2. Okay. Now if I'll go and proceed with this, and I will ask myself, what is omega 3 of u? Right? What should I do? Well, I have this three-dimensional space, and this is the, now not the area, but actually the volume below this hypersurface, two-dimensional surface, or triangle surface that we plotted before, and it should be an integral from 1 up to u divided by h bar omega 0, dn1, an integral from 1 to u divided by h bar omega 0, dn2, and an integral of dn3 goes from 0 to u divided by h bar omega 0. I have a triple integral now, but again I have some sort of constraint. What is my constraint? n1 plus n2 plus n3 is smaller than u divided by h bar omega 0. I do the same, exactly the same math that I have done before. I introduce this constraint into the integrals. Okay, I just introduce it. So for example, n3 goes from 0 up to u divided by h bar omega 0. I perform this integration. Okay, I obtain something that which is defined on both n1 and n2, and then I have a double integral, which is also simple. Eventually what I get is that omega 3 bar equals to omega 2 bar of u multiplied by what? By integration from 0 up to u divided by h bar omega 0 of 1 minus n divided by u h bar omega 0 to the power of 2 dn. Okay, I perform this integration and I substitute that omega 2 of u equals 1 over 2 factorial u1 of u1 bar of u, and I obtain from this integral that u3 bar of u equals to 1 over 3 factorial omega bar 1 of u. I can continue in this fashion again and again and again and again. The general formula, when I increase the number of n's that I have, going from 3 degrees of freedom to 4, to 5, to 6, to a general number of degrees of freedom, I will obtain that omega bar of n of u equals to omega bar of n minus 1 of u, it's actually easy to show, integral between 0 and u divided by h bar omega 0 of 1 minus n divided by u h bar omega 0 up to what power? Up to the power n minus 1 dn. From this formula, and using, again, the same relation, what is omega n minus 1? It's going to be omega n minus, it's defined in terms of omega n minus 2, omega n minus 3, omega n minus 4. You will see that that's a general formula is appearing. So what is omega n bar of u is omega bar of u n minus 1. This integral over here is what? 1 over n. 1 over n multiplied by omega 1 of u. So we have a relation that is omega n of u equals to omega bar n minus 1 multiplied by 1 over m omega 1 of u. Which the solution gives us that omega n of u is 1 over n factorial omega 1 bar of u to the power of n. Okay. This is what we get. It doesn't matter what is the dimension, okay, at some point, the number of states is the number of states for a one-dimensional system, which is basically u divided by h bar omega 0, and we have to take it to the power of n and divide it by n factorial. Let's write it down explicitly. Omega n bar of u equals 1 over n factorial u divided by h bar omega 0 to the power of n. Now, what we intended to compute the number of states in a small delta vicinity, okay, of the energy E. So, for how many particles? For n bar number of particles. Which basically means 3n bar number of degrees of freedom. So omega, without the bar, of 3n bar of u equals omega bar of 3n bar of u minus omega bar of 3n bar of u minus delta. Okay? We're taking a huge hypersurface, which is at 3n bar minus 1 dimensional, and we take a small volume near it, near this surface, and we compute how many states are in this small volume. It's not actually very small, it's very, very big. But this is our exact result. Now we are going to use omega bar n u in order to calculate this quantity, and also to calculate this quantity for different u. We're just going to, instead of u here, use u minus delta. And then we have our exact result, not exact, but our result for the number of states in the Einstein model when we have a general number of particles. Okay, let's see where it gets us. So omega 3n bar of u equals to 1 over n 3n bar factorial multiplied by u divided by h bar omega 0 to the power of 3n bar minus 1 over 3n bar factorial multiplied by u minus delta divided by h bar omega 0 to the power of 3n factorial. Okay, let's continue. So omega of 3n bar of u equals, let's take out this term. What we have, 1 over 3n bar factorial multiplied by u divided by h bar omega 0 to the power of 3n factorial. Inside here I have 1, right, minus 1 minus delta divided by u to the power of 3n factorial. Okay? And this is exact. So the number of states is this guy multiplied by this guy. But if n bar is very, very large, what is large? 10 to the power of 23. Where this guy goes? So 1 minus delta divided by u to the power of 3 n bar, where it goes as n bar goes to infinity. What is the limit? We should look on this term in this parenthesis. So 1 minus delta divided by u is a number that is smaller than 1 and greater than 0. Okay. So delta divided by u is greater than 0, smaller than 1. Then I have that 1 minus delta divided by u is a number that is larger than 0 and smaller than 1. So I have a number which is less than 1 to a huge power. So this actually goes to what? To 0. So 1 minus 0 is 1. Everything here goes to 1. When n bar is very large, all this term is going to 1. Okay? We don't need to take a derivative of this guy. We actually need to compute the limit, how it behaves when I'm taking the number of the degrees of freedom to be very large. What I'm getting next is that omega without the bar of 3n bar of u is actually equals to 1 divided by 3n bar factorial u divided by h bar omega 0 to the power of 3n bar, which means that when n bar is very large, what I obtain is that the number of states that I need to compute in order to proceed with the micro-canonical ensemble, 3n bar of u, equals exactly the number of states below the energy of u. Okay, this is what we got. Of and this is easy. Why it's easy? I don't need to compute all the states in a specific hyperplane or nearby the specific hyperplane. I just need to count all the possible states. It's much more easier than to compute the states that are very highly constrained. Okay. Taking this guy, I can go forward and compute the free energy, I compute the temperature, compute whatever I like. I just need to take the logarithm of omega bar instead of omega, okay, and proceed forward. Why we have managed to do so? We managed to do so only because we went with this extreme of very large number of particles. So we needed to compute a volume, a small volume around some sort of a hypersurface, and what we've seen is actually the small volume only in the area of the bounding hypersurface, it basically contains almost all the volume inside. Okay? So all the volume near, when we are going to a very, very, very high dimension, all the volume near the bounding surface is actually all the volume. Okay? This is an intriguing fact, but it's always true. Think about it. So we're used that, well, the area is actually what is inside and not what is near the boundary. And exactly the same in three-dimensional volume. Volume is what inside. There is only something small near the boundary. But this is not the same in very high dimension. Okay. So each time that we need to compute a volume, a general volume, so volume goes like in n dimensions, some constant n multiplied by the radius. Think about the volume of a ball. Radius to the power n. Right? So this is volume of some ball with radius r. What is the volume of a ball with radius r minus delta? Basically the same an, right? Except that I will have r minus delta to the power of n. When I'm going to subtract from volume r the volume r minus delta, what I'm going to obtain? I'm going to obtain that this guy is actually equals to an r to the power of n, and here I have 1 minus delta divided by r to the power of n. Okay. The same result that I had over here. And when delta is smaller than r, so I'm basically looking on only a small portion, but a finite portion, near the boundary, what I get, all the volume that is inside the small portion is actually all the volume. What we obtain that volume r minus volume r minus delta equals to what? To a n goes to infinity, a n r n, which is simply volume of r, of a ball of a radius r. So in any case, at some point we are counting states of free particles that are constrained only by what? By the global energy, a constant size of global energy. We can actually use this result when we have huge number of particles, because the only thing that is constraining them is this hypersurface, that the sum of all the different energies should be constant, right? Then we need to calculate, according to our algorithm over here, we need to calculate the volume below this hypersurface and subtract to it a volume that is below the same hypersurface but is slightly below. Okay? What we will get, that this volume, those number of states, is always the volume, it's always the volume that is restricted by the general energy. It's always like this. There are some corrections, but who cares, right? There are some corrections that are coming from this term. We don't really care about them. They are small, extremely small. Okay? Take n to be 10 to the power of 23. Delta is not 0, is a small number, but it's not 0. And you will see eventually that all the corrections that are coming from this term are negligible. And this can be performed in any situation when we have micro-canonical ensemble over free particles that are restricted only by the fact that the total energy is constant. All right. Now let us continue to more complicated, slightly more complicated ensemble. Any questions about this? So for micro-canonical ensemble, we have seen that there are some problems. The problems arise due to the fact that, well, you need to count states, and even when you don't need to count states, when you're going to this limit of very high dimensionality, you still need to integrate over something. So there is always this combinatorial problem that you are counting states. Even more, your original definition of constant energy doesn't really valid. Okay? You need to take not as a specific type of an energy, but small variations about these energies. And again, to count states. Can we provide a different ensemble, which is basically a different constraint for the system, such that eventually this counting process would be simpler? in some point, because we know that our connection to the macroscopical functions of state, like free energy, Helmholtz, temperature, is coming through the entropy. Okay? Entropy is the number of states, and in any case, we would be obliged, you're going to be obliged to calculate the number of states. But can we provide a simpler way of actually doing this? And this is how the canonical ensemble was born. Canonical ensemble. Okay. So in order to overcome all those issues of micro-canonical ensemble, we define a canonical ensemble. So the constraints of micro-canonical ensemble is constant volume, constant number of particles, and for the micro-canonical ensemble there was constant energy. Canonical ensemble is different. There is additional constraint, I'll write it in a second, but it comes from a physical perspective. What is my physical perspective of a canonical ensemble? So in canonical ensemble, I'm thinking of, well, I have a huge system. A bath, right? A reservoir. Inside this reservoir, the system that I'm actually interested in finding its energies, finding its behavior, it's sitting inside this huge bath, huge reservoir. This is my system. I'm interested in behavior of this system. What I'm assuming that my system plus the heat bath plus the reservoir, so those two systems together are a big, huge closed system that is behaving according to a micro-canonical ensemble, and the energy of those two systems together is constant. I'm assuming, and this is the third constraint of the canonical ensemble, that there is a thermodynamical equilibrium, or an equilibrium between my system and this system. Between the bath, between the reservoir, and my system. And if there is an equilibrium, I already know for thermodynamics that there are several things that are satisfied. And more importantly, what is satisfied? The temperature here is the same temperature of the bath of the reservoir. So the third constraint, constant temperature that equals to temperature of the reservoir. This is my third constraint. So again, what I have changed is constant energy of my system to a constant energy of the global system and an assumption of equilibrium between those two. But still I'm using micro-canonical ensemble description for the whole system. Why? Because I don't really know how the probability is behaving generally. But I do know, or assume that I know, how the probabilities of different states behaving in a micro-canonical ensemble. It's very simple. Micro-canonical ensemble assumes constant energy, and the probability for each state is exactly the same because all the energies are the same, equal. What we are going to do is use this micro-canonical description of the whole system and devise the behavior which is called the canonical ensemble behavior for my system over here. So what I'm doing, actually, when I'm saying, well, I have this big system and this small system, and I'm looking in a micro-canonical fashion on the sum of those two systems. What actually am I doing? I'm saying I have two systems and they are constrained. Okay? They are constrained. Think about a dice. So I have the dice. This is my dice. Can roll it and it can show me up to 6 numbers. It can show me 1, 2, 3, 4, 5, 6. Okay? And I also have another dice which is blue. And they're exactly the same. They look exactly the same. They show the behavior is very, very similar. And it also can show me numbers between 1 and 6. Each of the system can behave in a very random fashion, right? I just roll one dice, it shows me 2. I roll the blue dice, it shows me 4. It doesn't really matter. Now, what I'm doing by saying, actually, this is my system, and this blue one is a bat. And they behave in a micro-canonical fashion. What I mean by this is that I'm looking only all the outcomes when the sum of black plus blue equals what? Equals to for example 5. The total energy, I'm saying, is the outcome of the two dices. For example 5. And I'm constraining the behavior of all the dices, of the two dices, okay, such that the total energy or the total outcome is 5. Now, this is constraining my system. It can no longer show number 6, right? Because if it shows 6, the total sum of the black dice and the blue dice cannot show 5, because there is no number -1 over here. It also cannot show number 5 too, because if it shows number 5, blue one, it cannot show 0 because the sum is constrained to be 5. And again, it's not a possible state. I'm looking only on the states. I'm saying how my system can behave, on what outcomes am I actually looking, what are the outcomes that are allowed. The only outcomes that are allowed when the sum of those two dices equals to 5. So if I'm now starting to count different states of my system, I'm looking not on the global system, not on the two dices. I'm looking only on the black dice. I'm looking only on my system. The black one is my system, the blue one is the reservoir, and the total energy is constrained. I'm saying, well, now I have constraints also for my black dice. Because I know what are the possible outcomes of my black dice. It can show 1, it can show 2, it can show 3, it can show 4. 5 it cannot show, and 6 it also cannot show. If the black dice shows 1, what is the blue dice should show? 4. If it's 2, it shows 3. If it's 3, it shows 2. If it's 4, it has to show 1. Those are the only outcomes of the system. 1, 4, 2, 3, 3, 3, and 4, 1. It's a micro-canonical ensemble.
Well,
so
it should be 2.
Where? 2, right, sorry. Of course. Those are the only outcomes of the system. Okay? How many states I have as an outcome of the system? 4, right? Now it's a micro-canonical ensemble, so each outcome have exactly the same probability as all the other outcomes. So the probability of this pair is the 1, because this is a one single state, divided by the total number of the outcomes. What is the number of the outcomes? Is 1, 2, 3, 4. So the probability to get 1/4, if I'm looking on the system, under the constraint that the total sum is 5, okay? The probability to get this one is 1/4. The probability of this one is 1/4. The probability of this one is 1/4. And the probability of this one is 1 over 4. I can go backwards and say, what is the probability that the black dice shows 3? The probability, according to this calculation, is a quarter. What is the probability that the black dice shows 4 is again a quarter. Now, this is a very simple example when I have a dice for one system and a dice for the back. Let's go to a slightly more complicated system. My system is still one black dice, and the reservoir is 2 dices. Okay? And the reservoir is 2 dices. Right? So we have, this is the system that I'm looking on. And this is the reservoir. So how they are related to each other? The sum of all the dices is 11. Okay. So I'm looking on the black dice. It behaves somehow, right? It behaves somehow. But it's also related to all the other dice, the other 2 dices that are blue. In what a fashion? In a fashion such that the sum of all the 3 dices should always be 11. These are only the possible states. So it's not that my system can have any state. It can have only states that satisfy this global constraint. The global energy is constant. The number the sum of all the numbers is always 11. So let's see what are the possible states right now. My black dice can have 1, right? It can have 2, 3, 4, 5. It can have 5. Can it show 5? Yes, if it shows 5, there is still a possibility that the sum of the blues is 6. 5 and 6. So those are all the possible outcomes for the black cube. Now we're looking on all the different outcomes for the 2 blue dice. If I have possibility of 1, it can show 4, 6, it can show 5, 5, and it can show 6, 4. Okay? If the black cube is 2, it can show 3, 6, can show 4, 6, 4, 5. It can show 5, 4. And it can show 6, 3. Okay? Just try and compute the sum. 1 plus 4 plus 6 is 11. 2 plus 5 plus 4 is 11. The same goes for 3. 3 is, okay, so what is 3? Is 4, 6, right? What else? No, 3 is 2, 6, sorry. 2, 6, 3, 5, 4, 4, 5, 3, and 6, 2. Let's go to 4. So for 4 we have, well, large number. So it's going to be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. What we have left? 5 and 6. So for 5 we are at 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. And for 6, we have, this is the last one, 1, 4, 2, 3, 3, 2, and 4, 1. So those are all the possible states that the system plus the path can have. What are the states? 1, 4, 6, 1, 5, 5, 1, 6, 4. Okay, I take the number 1 here and add it to all the different tuples. Okay? So what is the total number of states? It's a micro-canonical system. What is the total number of states? Okay, the total number of states, I have to count all the different outcomes. So here I have, how many outcomes for 1? I have 3. For 2, how many outcomes I have? 1, 2, 3, 4. I have 4. For 3, I have 1, 2, 3, 4, 5. I have 5. For 4, 1, 2, 3, 4, 5, 6. 6 different states. For 5, I have 1, 2, 3, 4, 5. 5 different states. And for 6, I have 1, 2, 3, 4. 4 different states. I ask myself, what is the probability of obtaining 1? I throw my dice, I look only on the black one, and I ask myself, what is the probability that the black dice will show 1? So, what do I know? I know that all the different outcomes that I have written over here are equally probable. So 1 would appear only if 1, 4, 6 appears, 1, 5, 5 appears, or 1, 6, 4 appears. So it equals to the numbers of outcomes when I have 1, so it's 3, divided by the total number of states, by the total number of the outcomes. What is the total number of the outcomes? 3 plus 4 plus 5 plus 6 plus 5 plus 4. So it's divided by 3 plus 4 plus 5 plus 6 plus 5 plus 4. Which equals, so this guy over here is 27, this guy is 3. 3 divided by 27 is 1/9. I'm throwing my dice as I have this constraint, total energy constraint, and I'm looking at all the different outcomes. The outcome of 1 is 1/9. What is going to be the outcome of 6? The outcome of 6, probability getting 6 is the total number that are related to 6, which is 4, right? I have 4 different outcomes. Divided by the total number of the outcomes. So it's again the same sum over here. So it's 4 divided by 27. And now I can write a general formula. What is my general formula? Probability to get n equals number of states of the bus related to n divided by the total number of states. So this is, and this formula we're going to use as a general definition of a canonical ensemble. Because the canonical ensemble is what is exactly this generalization of micro-canonical ensemble. We're working on a small system, we have a constraint of the total energy, all the possible states are equally probable. So only thing that we must count is the total number of states. And for each specific state of the system, I need to count all the possible outcomes for the reservoir states. Okay? The bus, where do we stand? We have canonical ensemble. For the canonical ensemble, we have constraint of constant volume, constant number of particles, constant temperature, that equals to the temperature of the reservoir. This is our system, this is our reservoir, the temperature is equals. What else is actually equals? The pressure, right? The chemical potential. This is the stability relations that we've got. Very general stability relations that we got from thermodynamics. And what we have shown that if we have the situation of a general constraint, microcanonical behavior of a big system that is composed of two systems, right? So the probability for this system to be in a specific state equals to the probability of the number of states of the reservoir to be in all the different states that satisfies the constraint when this system in a specific state divided by the total number of states. So we will write it down in the following fashion. Fi, which is probability of the system to be in state I with energy EI. Okay. We know what it is. It is the number of states for the reservoir that are associated with the energy EI of the system. So it's just omega of E total minus EI divided by the total number of states for the whole system. For the system plus reservoir. This is omega reservoir. This is omega total of E total. So E total, the total energy of system plus reservoir. EI is the energy of the system. Omega reservoir is the number of states. It's the different number of states that the reservoir can be in, and it can be a huge number of states because the reservoir is large. Okay? Divided by the total number of states of this guy plus our system. So now you can tell me, well, Stas, you haven't gotten us really far. Why? Although you have a very clear definition of the probabilities, okay? This is the definition of probabilities. Beforehand, it was just 1 over the total number of states. This is a micro-canonical description. Canonical description is 1 total, the different number of states, multiplied by the states that are associated with the reservoir. You still need to count all different numbers of states. Okay? Of the total system, of the small system, of the reservoir. And again, it's hard. Again, we're sitting in some sort of a combinatorial problem saying, we need to count states. We need to count states. Have I gained something? Actually, what we are going to show, when the system is large, and even when not so large, this definition produces something that is much more simpler than the procedure of counting of states that we have encountered before. Okay. And what we are going to develop now based on this definition over here and the definition of entropy is the most important formula of statistical physics of equilibrium. So what exactly we are going to do now? we want to take this guy and represent this Fi in terms of entropy. So entropy, I remind you, we will have an entropy of what? Total entropy. What is the total entropy? Is K Boltzmann ln logarithm of omega total. Okay. This is S total. And we also have S reservoir. What is S reservoir? It's again K Boltzmann ln of omega of reservoir. Now here we also can introduce entropy as the function of entropy. So S total we are going to have here E total. It's K Boltzmann ln omega total of E total. And as reservoir, we're looking on reservoir of E total minus EI. We'll have here E total minus EI equals to K Boltzmann log of omega reservoir of E total minus EI. It's the energy associated with the bath. It's the energy that associated with everything. So we can write Fi, instead of using the number of states, we're going to use the definition of the entropy. Okay, so Fi equals, so omega reservoir of E total minus EI equals to exponent of what? Of S reservoir of E total minus EI multiplied by 1 over K Boltzmann. This is the term over there. Now what we have for omega total of E total, you're using this definition. It's simply exponent of 1 over K Boltzmann S total of E total. Let's define U as the average energy of the system. What is U? So the energy of my system, well, it can be E1, E2, E3, all different states. And I'm saying, well, because it can be in different states, I can also define an average of all of these energies. And I call it U. The next step is to say, I remember something about entropy. Entropy is what? It's extensive quantity. Do you remember that entropy is extensive quantity? Which is basically saying that S of E total, S total, E total, it equals to what? The entropy of the system that has an energy of U plus the entropy of the reservoir that has an energy of E total minus U. We know that entropy is an extensive function. So we count all the states and it's related to the states. Okay? So we count the states and we take a logarithm. And we know if we do this for the whole system, it should be the sum of what is the entropy of the reservoir and what is the entropy of the system. After I have done this, I can ask myself, what is the entropy of the reservoir, of the heat bath? I can write it down as S of reservoir of E total minus EI. Where I'm going here, plus EI minus U. Okay, or I can write it down that S reservoir of E total minus EI equals to S reservoir of E total minus U plus U minus EI. Okay. Can add and add some general energy U and subtract some energy U. Great. The next thing is to actually take a Taylor expansion of this entropy. I want to Taylor expand this guy around what? Around E total minus U. So S reservoir of E total minus U plus U minus EI equals to S reservoir of E total minus U plus dou S reservoir dou E, okay, multiplied by what? U minus EI plus all the different terms that I have over here. Okay. But what is the ds reservoir dE? It's S reservoir E total minus U plus 1 over T, right? The derivative of the entropy with respect to the energy is the definition of the temperature. U minus EI, okay, plus all the different terms. What are those different terms? It's the second derivative of the entropy with respect to the energy, and the third derivative of the entropy with respect to the energy, and the fourth, and etc., etc., etc. But the first derivative of the entropy with respect to the energy is the temperature, is a 1 over T. And what we have assumed, T is constant. It doesn't really matter in what energy I'm sitting, the temperature is constant. Okay? So the temperature of the reservoir and the reservoir with the system, the temperature of the reservoir is constant. So all of those additional terms that I have over here are simply 0. Okay? This is the derivative of a constant function. So I don't have anything here left. The moment I got here, okay, I can basically say that S reservoir of E total minus U, which was S reservoir of E total minus EI, equals to S reservoir of E total minus U plus 1 over T U minus UI. So Fi equals to E over 1K Boltzmann. And here I'm going to say, well, what I have here is just simply S reservoir of E total minus EI. But S reservoir of E total minus EI equals to this guy, and this guy equals to what I have over here. So write it down as S reservoir of E total minus U plus 1 over T U minus EI. On the other side of the fraction, what I have is E of 1 over K Boltzmann, and I have there S total of E total, but S total of E total equals to the entropy of the system, okay, plus the entropy of the reservoir with what energy? E total minus U. So here I have right, instead of the entropy of the total system, as S system with average energy U plus S reservoir with what energy? E total minus U. what eventually I obtain? That Fi equals 2. So S reservoir and S reservoir are disappearing. And I have over there e to the power of minus, 1 over k Boltzmann T U minus T S system of U, okay, multiplied by e to the power of minus 1 over k Boltzmann T of E I. I have two terms. One term is related to the average energy, the entropy, and actually what this guy over here, it's a free energy, Helmholtz free energy. This is what stands over here, multiplied by something which is very simple. Do I need to know what this guy is? The claim is not. Why not? Because everything should be normalizable. I know that sum of I, Fi, should be 1. Probabilities to be anywhere is 1. So a sum of I, e to the power 1 over k Boltzmann T, U minus T S system of U, multiplied by 1 minus k Boltzmann T, Ei, equals 1. And I obtain that what? That e to the power 1 over k Boltzmann T U minus T S system of U multiplied by the sum of I E minus Ei divided by k Boltzmann T equals 1. And what I write over here is that e to the power 1 over k Boltzmann T of U minus T S of U equals to 1 over the sum of I E minus Ei divided by k Boltzmann T. I call this guy a sum of I E minus Ei k Boltzmann T Z, partition function. And eventually what I have obtained is that the probability to be in some specific state, I, is simple factor of exponent of minus Ei divided by k Boltzmann T. All of this divided by C. And this is the most important function, most important formula of statistical physics of equilibrium. When I have a system which is composed from many different states, the only thing that I need to perform in order to compute the probability to be in a specific state is to compute the partition function and the probability of computing this fraction over here. The only thing that I need to know are energies. What are the different energies of the system? I forget about the bath. The only thing that I keep about the bath is the temperature. The temperature of the bath that stays constant. I'm not counting states now. I'm only looking, what is the probability of this state? Oh, I only need to know its energy. What is the probability of that state? I only need to know all the energy, that energy. I, of course, need to calculate this sum, but this is just simple sum without any constraints, right? So instead of counting different states with specific constraints, what I have now, I'm just looking on different energies of different states and summing them up. And that's it. Very, very, very simple and very, very, very powerful. Okay. Now, what is the relation between the partition function and some macroscopic functions, macroscopic function of states? Well, what is U minus Ts of U? Is free energy, Helmholtz free energy. So what we have here is that, look at this guy, E to the power 1 of K Boltzmann T of F equals 1 over Z. And I can write this down as F equals minus 1 over beta log of Z, whereas beta is 1 over K Boltzmann T. I have an exact relation for a macroscopic function of state, right? Because if I know the Helmholtz free energy, I can compute all the other auxiliary functions. I can compute Gibbs free energy, I can compute enthalpy, I can compute their derivatives, compute pressure. Doesn't really matter what, I know everything. The moment I know what is the partition function, or even simpler, I know what are the different energies of my system, I know everything. And I know how to construct macroscopic function of states based only on what? On the microscopical picture. Only the different states of the system. This is the only information that actually needed. Right? And we got really, really far from the micro-canonical ensemble. Why? Because we don't need to calculate states now. We need just to recognize that there are states. Now, one can maybe ask how you managed to do this. How actually you went from description with specific states, specific constraints, counting into just recognition, well, this state is this probability, and it's only related to the energy. What is this state is really, really rare? How do I know that it's really, really rare? From the definition of the states, from the contribution of the energy. When I know that the state is really rare, when its energy is really, really high. Why it's rare? Because if its energy is really, really high, the energy of the bath should be really, really low, or some low, because the total energy must be constrained, okay? And the temperature is kept constant, and it's very, unnatural situation. And this unnatural situation comes due to the fact the exponent of something really, really large and negative is very, very small. So I'm allowing for all states. This is why I don't have this combinatorial problem. I'm allowing everything. Every state is possible. Okay, but there must be some payoff. And this payoff comes in this factor of e to the minus the energy. This state is very, very obscure, but it's possible. I still need to count it down. But I should take a weight. What is the weight? Very small number. Now, how we go from here in actually calculating different observables. So let's calculate the average energy. What is the average energy? The average energy is sum of I, EI, FI. Okay? Which is simply what? Is sum of I, EI, e to the minus beta EI divided by the sum of J, e to the minus beta EJ. Okay? This is Z, this is the Boltzmann factor. Okay? This is all the different energies. The average energy is the probability of each energy multiplied the energy itself. And what we have over here, we can take the sum out. We have 1 over j e to the minus beta ej, and we left inside with 1 over I ei exponent of e to the power of minus beta ei. Now look on this guy. I need to sum it up. But I recognize something. I recognize specifically that each term is in this sum, which is ei multiplied by the exponent of minus beta ei, is equals to what? Ei e to the minus beta ei is 1 over beta. I'm sorry. It's minus d beta of e to the minus beta ei. Take the derivative with respect to beta, okay, of the exponent. What I will have? I will have minus ei multiplied by e to the minus beta I. I have additional minus over here, so it's fine. Alright, so now I can write all this function as u equals 1 over sum of j e minus beta ej multiplied by sum of I minus d beta of the exponent of minus beta ei. Alright? So I just replaced each term of the ei e to the minus beta ei with the minus the derivative with respect to beta. It's a finite sum. It's a very big number of states, but it's still finite. I can take the derivative with respect to beta outside. So I have 1 minus sum of j e to the minus power beta ej multiplied by minus d beta of what? Of a sum of I e to the minus beta ei. Great. But what is the sum of I e minus beta ei? This is the partition function, the most important object that we have right now. And what is 1 over sum of j e minus beta ej? Is again a partition function. So all of this equals 1 over z minus d beta of z. And what is 1 over z d beta z? It's simply 1 minus d beta of a log of z. We obtain that the average energy is also given by the partition function, or the derivative of the partition function. U equals minus d to the d beta of 1 of z. And what else we can show? Well, we know that ln of z equals minus beta f. And if we use this, that u equals minus d to the d beta of minus bf, and we perform all of this differentiation, we would obtain that u equals to f plus ts, where what we are using, we're using that df dt equals minus s, df dt equals minus s, and eventually we obtain that u equals f plus ts, and we already know this. And in some sense we convince ourselves that we are right. There is a constituency between this definition of the probabilities and the average value of the energy. Okay, so we came to a situation where the only thing that we need to perform is to recognize for the system what are the possible energies and use this this definition for the partition function, calculate the partition function, and we need the probabilities, we can count them. But we don't really need them in order to compute macroscopic properties. Because the moment we know what is the partition function, we know what is the free energy, we know what is the average energy, and that's it. The moment we know macroscopic function of states, we can calculate all the different macroscopic properties of the system. And we started with a microscopical description of what are the different states, microscopic states of the system. Okay. And this is the great power, great artillery of statistical physics, statistical mechanics, equilibrium statistical mechanics. The only thing that you need to know is the Hamiltonian, the energies of the system. The moment you know this, everything else is set. It's sometimes really, really hard to do this, right? But if you know all the different energies of the system, you only need to factorize them, sum them up. That's it. If you are in a canonical ensemble. Now, is this canonical ensemble physically satisfied? The answer is yes, it does. Because think about almost every system that we're trying to investigate experimentally. It's not big, small, have a huge room around it. The temperature of the room is basically constant, okay? Because this small object that we're looking on is small, although it might contribute something to the room, but it's really, really small. So this assumption of a constant energy in a big heat bath, it's actually something that makes sense, and it's actually that what happens in reality as far as we understand for equilibrium systems. So in equilibrium, we know how to treat the system, as long as the constraints are satisfied. What are the constraints? Constant temperature and constant number of particles, constant volume, and we will get to the situations when we also neglect the constraints of constant number of particles. They're still here. Now, why else this property and this property is very, very strong? Well, let's think about free particles, gas of free particles, or particles that are not interacting with each other, okay? Like something like the ideal gas. Okay. So any type of a situation when each particle can have different states, different energies, and it's completely independent, those states are completely independent from all the states of all the other particles. So again, you have a system. It's composed from a big number of particles. Take, for example, the Einstein model or the two-state model. Okay. And what we need to show is, well, what are the energy of the total system, of all the n particles? They don't care about each other. They completely do not care about each other. What we will show that there is a general prescription for such type of models. The models for that display a system that is just the sum of a lot of particles, independent particles. They do not see each other. And we will see that in a canonical prescription, the moment that we have such a system that's composed of independent particles, we can say a huge number of things almost immediately about the system. And we already know how to solve such systems from start to end. Now this is actually, and what we will see that it doesn't really matter if the energies of the different particles are the same or they're somewhat different. The only thing that matters is that all the different particles are independent. And then we will need to treat each particle separately. Now, how this situation is possible? So, well, maybe it's possible only for the ideal gas, right? In the ideal gas case, the particles are not interacting, they do not see each other, all their energies are possible. In most other situations, the particles are interacting somehow. Okay? They have strong interactions, they see each other, they have specific constraints, they can push each other, etc., etc. But what we know from regular classical mechanics, what we were trying to do there in regular classical mechanics. So what we were trying to do is, if we have system with 2, 3, 4, 5, doesn't really matter how many particles, is to find a new coordinates, new description of the system by using Hamilton description, using Hamilton angle action variables. It doesn't matter. The Hamiltonian prescription is what is actually to take a system with specific correlations, the specific interactions, and represent the system in such a way that the interactions will disappear, that we will have free particles, maybe harmonic oscillators, and it's always possible to do this. This might be very, very, very complicated, but we can always think philosophically that there is a transformation such that for this transformation, what we will see degrees of freedom, degrees of motion that are not correlated with each other. And when I'm saying particles, what I actually mean, oh, those are not real particles, but I'm saying that there are transformations, spatial and temporal transformation, such that in those new coordinates, those particles are free. The energies might be changing by some crazy law, but they do not interact. So in regular classical mechanics, what we were trying to perform is to take a complex system, and actually make a transformation into what? Into a system that the coordinates, geometrical coordinates, are of degrees of freedom that are not interacting. The same goes for statistical physics. The goal in statistical physics is to take a complex system and somehow make it representable in new coordinates, in new particles. It might be not particles, it might be waves, it might be excitations, whatever we call it, but particles that are not interacting with each other. And the moment we have done this is why it's called statistical mechanics, because it's done in a statistical way, but the same goal as mechanics. The moment that we have done this, we are creating a system of free particles, non-interacting particles, and this system is always solvable. The system of ideal gas is always solvable. And what we will see right now, how we take, if we already have a system of a non-interacting particles, okay, how we can actually solve it completely and exactly. Okay. So what we have right now is epsilon, I, and j. I is particle number I. And when I mean particle, I can mean excitation, a wave, something which is not interacting with anything else. Particle number I. J is Ji. The state Ji of particle number I. So what is epsilon? Iji is the energy that is associated with the J state of particle number I. I have n particles. Each particle have its own general states, right? It has its own general states. I'm sorry. And I need to count all of them. Right? So if I'm going to compute the partition function, I need to take into account all the possible energies. The only thing that matters to me is that if particle I is in state J, it doesn't really says anything what is the state of particle K, because they are not interacting. Each particle can be in whatever energy it likes. I don't care. So this is the picture of non-interacting particles. There's a lot of energies, and those energies and the states of different particles are completely independent of the states of all the other particles. What is the partition function for such situation? So what we must count on? We must count on all the possible energies, which is saying we must count on all the possible j slides. So j1 and j2 and j3, etc. Of what? Of the Boltzmann factors. What is the Boltzmann factor? E to the minus beta total energy. What is the total energy? So let's assume an energy of a specific state. The first particle is in state J1. The second particle is in a state J2. The third particle is in a state J3, and we have a big sum over here. So we take all different particles. We are saying you now in state J1, you now in state J2, you now in state J3. We sum all the different energies. We take an exponent of minus beta, this big energy, and say this is a one summand of the total sum of that represents the partition function. And we must sum over all possible states. Remember, what is the partition function? It's a sum of all possible states. All possible states of 1 and 2 and 3 and 4 and everybody all together. Okay? Which just simply means J1, J2, E minus beta epsilon 1 J1 multiplied E minus beta epsilon 2 J2 E to the minus beta epsilon 3 J3, etc., etc., etc. Now, here I have a sum over states J1, J2, J3, J4, J6. I can say, well, this sum is what? Is a sum over J1 and a sum over J2 and it's a sum over J3, right? And I have a lot of sums up to Jn of what? Of E to the minus beta epsilon 1 J1 multiplied E to the minus beta epsilon 2 J2 multiplication up to what? E to the minus beta epsilon n Jn. Let's take this epsilon outside of all the sums. This is just J1 epsilon minus beta epsilon 1 J1. And here I can take this factor out, and it will be sum of J2 epsilon minus beta epsilon 2 J2. And here I have J3 epsilon minus beta epsilon 3 J3 up to sum of Jn e to the power e minus beta epsilon n Jn. So I have a multiplications of sums, but each sum is what? Is the partition function of a single particle. Remember, I defined the partition function for a global system. Now I'm looking, well, this is actually a partition function that consists of only one single particle and all the different states of these particles. Exactly goes for this guy and this guy and this guy. So what do I have in common? I have that Z equals Z1 multiplied by Z2 multiplied by Z3 multiplied by Zn. Write it down in J equals from 1 to n Zj. So when I have non-interacting particles, the only thing that I need to do is go into each one particle, compute the partition function for this specific particle, this is Z1 or Z2 or the Z3, and make a big multiplication. if I want to compute now the free energy, okay, the free energy of this big system, what should I do now? F equals minus 1 over beta ln of z. Which equals minus 1 over beta ln of pi, j goes from 1 till n of zi, and it equals minus a sum of j from 1 till n of 1 over beta ln zj, and it equals to the sum of j from 1 till n of a j. If I'm going to the free energy picture, it's just the sum of the free energies. So instead of treating a big macroscopical system, I'm treating a lot of simple microscopical systems, and each microscopical system I'm looking from the perspective of a canonical ensemble, right? Because the only thing that I need to know is this guy, Zi equals to the sum of E minus epsilon I Ji, and Ji goes from 1 to whatever number I have there. So it's quite interesting, right? Instead of looking on something really big, I'm looking on something really small, and I'm only concerned with the energies of this guy when it's small. This part called factorization. And the only thing that I needed in order to produce this factorization is what? I had two assumptions. One, the total energy is a sum of all the energies of all the particles. Two, all the particles are independent of each other. So the moment I can produce some coordinates and some particles, I have a complex system, right? But in the moment that I'm actually capable of producing a transformation, it can be very, very complex, but a transformation to a system where all the degrees of motions are independent, I can solve this. And well, it's easier said than done, exactly as in classical mechanics. In classical mechanics, we've seen only a few examples that we can solve. Same in statistical physics. There are only a few examples that we can find such a transformation and solve the system. But the moment we have done this, everything is known. We will see it in an example. If you have a really complicated problem of an important system, that is, representation of which involves correlations of a lot of particles, and you are capable of finding a transformation that takes you from the representation of interacting particles to a non-interacting particles, when you then can do this factorization, you'll get a big prize, right? We have a few examples in the history that it was performed, and each time that it was actually done for an important system, people got a Nobel Prize. The most known example is the example of superconductivity, right? So in superconductivity, the electrons are fermions, right? And they are strongly interacting with each other. What you can actually do, this is Bardeen-Cooper-Schrieffer theory for superconductivity, BCS, is for low temperatures, you can make a transformation. Looking instead of electrons, you're looking on pairs of electrons. Those are your new particles. They are forming Cooper pairs. And those Cooper pairs eventually can be non-interacting, or they can be represented as a sum of harmonic potentials. So you take a particle, which is a fermion, you make a presentation of new particles that are bosons, you represent everything as a non-interacting picture, you solve it, and you can actually prove that why you can obtain superconducting states, basically a state that has no resistivity whatsoever. And you can use this statistical physics in order to describe what's going on there. right? So there is a very, it's a very interesting transformation. There are a few of those that we know. But each time that we find something like this, usually means that we are capable of solving a very, very, very hard problem. And this is the goal, this was the goal in classical mechanics, and this is the goal in statistical physics. To take a system which is hard, which is interacting, which is complex, find a transformation, find a representation where it has non-interacting picture, and when you have non-interacting picture, you can solve everything. Hopefully we will come to a general prescription that was found in the 70s called a renormalization group, where you can actually make a progress and understand how such transformations are created. But back to our thing over here. In the special case when all the particles are identical, if I found a situation where the factorization is true and the particles are identical, what we have Z equals pi from j from 1 to n, zj, which is basically saying z1 to the power of n. So if the particles are identical, the only thing that matters to me is the behavior of a single particle. Afterwards, I want to compute the partition functions of the whole system. I just take one single particle to the power of n. So instead of treating a macroscopical picture, I'm treating one single particle and all the different states of this particle. Okay, so let's see two examples. The examples that we already have seen are the example of two-state model and Einstein model. So for the two-state model, so first I will write down when factorization is possible. One, the energy is a sum of all energies of all particles of the energies of all particles. Two, the particles are independent. Okay. Those are the only two assumptions that I need in order to describe by using this factorization procedure over there. So let's go to the two-state model. N particles. Each particle have only two energies, 0 or epsilon. This was our model, right? And we worked, well, a little bit hard, not too hard, in order to describe the behavior in a micro-canonical ensemble. Let's do this in a canonical ensemble. We know that what happens over there. The particles are independent. They don't care about each other because we are looking in a canonical description. And the total energy, because it's always a sum, at least here, it's a sum of all the energies of all the different particles. So what is the partition function? Z1. We need to look only on the behavior of one single particle. What is the partition function? It's easy. We are going to sum over the Boltzmann factors with each energy. So there are only two states. There are only two energies. One is 0, one is epsilon. So what is the Z1 is e to the power minus beta, the first energy, which is 0, plus e to the minus beta, the second energy, which is epsilon. Are there any other energies? No. We are done. So Z1 is simply 1 plus e to the power minus beta epsilon. Okay. What is the partition function? Z is Z1 to the power n, which is simply 1 plus e to the minus beta epsilon to the power n. What is the free energy? F 1 over beta ln of 1 plus e to the minus beta epsilon n. Okay? Which is simply minus n divided by beta ln of 1 plus e to the power minus beta epsilon. If I had to solve the same problem for 3 states or 4 states, would it be any more difficult? No, because what I had to do is to add here another 2 terms, or 3 terms, or 4 terms. It doesn't matter. It's very simple. If I had also here epsilon 2, okay, so I would add only here another term, e to the power minus beta epsilon 2, and I'm done. I would have Z1 1 plus e to the power minus beta epsilon plus e to the minus beta epsilon 2. Take it to the nth power, take the logarithm, you're done. This is very simple in this representation. If I had to do 3 particles, or 3 states in the micro-canonical ensemble, it's a nightmare. It's a combinatorial nightmare. And the more particles that I have, and the more states that I have, the darker and darker becomes my nightmare. Right? It's really, really hard. In the canonical representation, it's simple. We've done it in a second. Okay? The same goes for the Einstein model. What happens in the Einstein model? It's similar to the what? To the two-state model, only, well, the definition of the energies are different, and each particle can have infinite number of energies. So Einstein model, what we have in the Einstein model, En equals n to the power of n h bar omega 0. N goes from 1, 2, 3, 4, to infinity. And we have 3 n bar particles. Okay? And I ask myself how I write the partition function, how I write the free energy for this system. The particles are independent, they don't care about each other. There is no constant energy constraint. So the only thing that I need to count is Z1. What is Z1? Is, again, I just go and count all the possible energies that are associated with one single particle. So what is those possible energies? E to the minus beta, the lowest energy is 0, plus e to the minus beta, plus the next energy. What is the next energy? Here I have 1. Is 1 h bar omega 0, plus the next energy, e to the minus beta, 2 h bar omega 0, plus the next one, e to the minus beta, 3 h bar omega 0. And I continue this to infinity. What is this looks like? It's a geometric sum, right? Look at this guy. What we have here is Z1 equals e to the minus beta h bar omega 0 to the power 0 plus e to the minus beta h bar omega 0 to the power 1. Right? Plus e to the minus beta h bar omega 0 to the power 3. Okay? And we can continue this. 2. We continue this on and on and on and on. What we get is that Z1 is 1, the first number, divided by 1 minus the mutual multiplicator. What is our multiplicator? E to the power minus beta h bar omega 0. E to the power minus beta h bar omega 0. We computed Z1. We know what is Z general. It's just Z1 to the power 3n bar. Right? What is Z? Z is just simply Z1 to the power 3n bar equals 1 divided by 1 minus e to the power minus beta h bar omega 0 power of 3n bar. We want to compute the free energy. It's again very simple, minus 1 over beta log of all of this guy. 1 over 1 minus e to the power minus beta h bar omega 0 power 3n. So the free energy is simply minus 1 over beta 3n bar 1 over 1 minus e to the power minus beta h bar omega 0. That's it. Very simple. Give me any problem that I have free particles that are not interacting with each other. Describe to me or make me find for a single particle what are the different energies of this particle. The moment I have completed this task, I actually know everything about the statistical behavior in the canonical representation of the system. Because factorization holds, and this is the end of the game. Okay? We can always do this sum. Always. It's not difficult just to write the sum. It's a simple sum. That's it. And it doesn't really matter how many particles I have inside because they are not interacting, and it's always a power to the number of particles. So the big goal always is to take a system which looks somehow and represent it in a way that it looks as the particles are not interacting with each other. We will end up and we will continue the canonical and grand canonical ensemble next week.